name is Ibra.
And my name is Emeka, and this is our chemistry concepts video presentation. Electromagnetic radiation is a form of energy that travels in waves through electric and magnetic fields. Due to its broad spectrum, it's divided into different categories based on its wavelengths. Long wavelengths are like radios, shorter wavelengths are like X-rays. There are visible and invisible portions of electromagnetic radiation. The visible portion shows as light, which ranges from 700 to 400 nanometers, which is from red to violet. Longer wavelengths travel longer distances, which is why radio waves are used for communication, allowing you to listen to a radio station miles and miles away. Examples of invisible waves are like radio waves, X-rays, microwaves, or radiation that your phone emits. The highest part of an electromagnetic wave is the crest, and the lowest point is the trough. The distance between the crest and the trough of adjacent waves is called wavelength, and the number of waves passing through a point within a certain time is called the frequency. Longer wavelengths have lower frequencies, shorter wavelengths have higher frequencies, and frequencies are measured in hertz, which is the number of waves per second. An X-ray is going to have higher frequency than radio waves due to the fact that an X-ray has a shorter wavelength. All electromagnetic radiation travels at the speed of light, and the electromagnetic spectrum is the range of electromagnetic radiation, which ranges from waves with the lowest frequency, which can be waves that wouldn't impact us like radio waves, to waves with the highest frequency, which could be the most dangerous ones to us, like gamma rays. Waves with high frequencies also emit the most intense heat compared to waves with lower frequencies, which is why when a nuclear weapon is launched, anything that's in its vicinity burns up.
Alright, this is energy equations, and for the first one I'm going to start with energy. It says calculate the frequency. My first question says calculate the energy of a photon with a frequency of 275 gigahertz. So on this, which is kind of my cheat sheet, the equation for energy is frequency times, heck, I don't know his name, but it's somebody's theory, I'm gonna be honest. But so E equals velocity, which is 275 gigahertz. But because it's in gigahertz, we have to bring that down to hertz. So 275 gigahertz. If you go over to this chart right here, which is from last unit, gigahertz is 10 to the 9th power. So 275 times 10 to the 9th power. And then you want to do S minus, because that's the value for it. Times, and then you have to do, I think his name's I don't know, somebody starts with the H theory. H's theory is 6.26 times 10 to the negative 34th power. 6.62. 10 to the negative 34th power. You multiply that, and you will get this is what I'm doing on calculator. 275 times 6.626 equals 1,822.15. So equals 1,822.15 times. And then you have to basically, when you're multiplying exponents, you have to add them together. So 9 plus negative 34 is going to be to the negative 25th power. Okay, now you can't just leave it like this. You're going to have to move the decimal point right here. So that's 1, 2, 3. You have to add it right here. So then you'll have 1.822. I'm gonna round the 5 up, so I'm just have 1.8222 to the negative 22nd power, and that's how you do the energy equation. after doing the last problem, I realized that I didn't have I didn't write the values down for Planck's constant or the hertz. So this is 275 hertz times 10 to the ninth power, and then this is Planck's constant, and this behind this you write joules per second. Joule times S. So you write joules per second. 1 over S minus, and then you have joules per second right here. When you multiply them together, you multiply joules per second over seconds. You take this out, and the energy what you're left with is basically 1.8222 to the negative 22nd power joules, and that's the energy. My bad, forgot to add the values in. Okay, so for number 2, we're doing a speed of light equation, and the question says, what is the frequency of a photon that has a wavelength of 1.5 times 10 to the negative 8th power? Now, the energy equation is basically, or the speed of light equation is speed of light is equal to frequency and wavelength. So we already know what the speed of light is. I have the equation on the back of this sheet. We know what the wavelength is, but we're trying to find the frequency. So we're gonna have to divide the speed of light by the wavelength to find the frequency. So speed of light formula is 3.00 times 10 to the 8th power meters to seconds. And then you divide that by 1.5 times 10 to the negative 8 meters. 3 divided by 1.5 is 2. So you put 2 right here times. When you're doing exponents, you're subtracting the exponent, you're subtracting the division. But because this is negative, you're adding, because a negative minus a negative is a positive. So that's 10 to the 16th power. And that's seconds, and this is the frequency right here. Okay, so for number 3, we're going to determine the wavelength of a photon that has a frequency of 95 megahertz. So let's make sure I did all the values for this. Okay. So in order to do this, well, up here, we already know that the formula for the speed of light is 3 times 10 to the 8th power milliseconds, and we know that speed of light is equal to frequency and wavelength. But the actual symbols look something like this. And this would be C, so it'd be C equals F, this stuff right here. But So in order to do that, we're gonna have to divide the frequency from the speed of light to find the wavelength, and that's it. So we're first gonna have to turn 95 megahertz to hertz. So if we take our little sheet right here, we see that mega is 10 to the 6th power. So this is how we're gonna do this right here. 3.00 times 10 meters per second divided by 95 times 10 to the 6th power. Okay, so what we're gonna do is divide 3 by 95. Pull out the calculator here. 3 divided by 95 equals 0.0317. We're gonna round up to 0.0316. Some people. .0316 times 10 to the 2nd power. The reason why it's 10 to the 2nd power is because when you're dividing an exponent, this is basically subtraction. This isn't a negative, so we're subtracting 8 by 6. Now, we can't just leave it like this. We're going to have to move this up so it could equal a non-decimal number. So 1, 2. Sadly, we only have 10 to the 2nd power, so this is gonna have to go away. It's gonna go into this to make it a full number. So we're gonna get equals 3.16, and yeah, 3.16 meters. Let's not forget the symbols, and that's it.
Well, for 3, we have quantum numbers. Quantum numbers are like the address of an electron in an atom. It tells us where it is and what it's doing. There are 4 quantum numbers. The first one is a principal quantum number, and that's N. It tells us the main energy level or shell of the electron. It can be any positive integer. The bigger the N, the higher the energy, and the farther the electron is from the nucleus. The second quantum number we have is angular momentum quantum number, and that's L. It tells us the shape of the orbital where the electron is found. It can be any integer from 0 to n -1. Each value corresponds to a type of orbital. L0 is an S-shape, holds 2 electrons. L1 is a P, dumbbell shape, holds 6 electrons. L2 is D, it's a clover shape and it holds 10 electrons. L3 is F, it has a complex shape and it holds 14 electrons. For 3, we have a magnetic quantum number, and that's ML. It tells us the orientation of the orbital in space. It can have any integer between -1 and +1, including 0. For 4, we have spin quantum number, and that's MS. It tells us the spin direction of the electron. It can only be +1/2 or -1/2. This means the electron is in the same orbital, must have opposite spins. In nursing, quantum numbers helps explain how atoms bond and interact, which is important for understanding drug interactions and molecular behavior in the body. For 4, we have electron configuration. It shows how electrons are arranged in an atom's orbitals. It is used in nursing to help explain chemical behavior and important in drug design. So we have 3 examples. We got sodium. So sodium has 11, atomic number of 11. So 11, that would be 1. That's 2. 2 is 2. 2p6 and 3s1.
And then we have carbon. Carbon has an atomic number of 6. So that would be 1 S 2 2 S 2 and then 2 P 2. Therefore, our third example, we have calcium. Calcium have an atomic number of 20. So that would be 1 S 2 2 S 2 2 P 6 3 S 2 3 P 6 and then 4 S 2. So there's your electron configurations. So next we have the Lewis-Dot structure. The Lewis-Dot structure shows valence electrons around atoms to illustrate bonding. It helps nurses use to understand molecular structure affecting drug interactions. So first we got methane, CH4. So we do 8 since this has 4. 1 C. And then next we have water, H2O. So we have H. So then we put dots on top and dots on bottom. And then lastly we have ammonia in H3. So that'll be 3 H's. And the dots on the bottom. So this is your Lewis-Dot structure. So next we have the Vesper theory. It ties in with the Lewis-Dot structure. The Vesper theory is a way to predict the shape of a molecule based on the idea that the electron pairs are around a central atom and they repel each other to stay as far apart as they can. So for our examples, we have methane. Methane is a tetrahedral, and then we have water. Water is a bent or angular, and then we have ammonia. Ammonia, and then we have a triangular pyramid.
For number 7, we're doing chemical nomenclature of molecular and ionic compounds. So, an ionic bond is when the metal gives up its valence electrons to a non-metal. This turns the metal into a cation. The metal turns into a cation because this gives the metal its positive charge. I fucked up. Number 7, we're doing a chemical nomenclature of molecular and ionic compounds. An ionic bond is when the metal gives up its valence electrons to a non-metal. This turns the metal to a cation. This gives the metal a positive charge since it has more protons than electrons, and turns the non-metal to an anion. The non-metal absorbs the valence electrons from the metal, turning it into an anion since it has more electrons than protons, giving it a negative charge. Non-metals need to form complete oscillates or octets. So in order for them to do this, they must combine with one or more metals, depending on how many valence electrons the non-metal has. Oxygen will need to bind with 2 sodium ions to form a complete octet, due to the fact that oxygen has 6 valence electrons and sodium has 1. A nonmetal needs 8 valence electrons to form a complete octet. A covalent bond is when two nonmetals share a valence electron in order to have a stable configuration, aka have 8 valence electrons. An example of this would be oxygen combining with 2 hydrogen atoms to become stable, sharing the 8 valence electrons between the 3 atoms. Or chlorine and fluoride coming together to form chlorine fluoride, which completes the octet for both of them, because they both share that last valence electron, so they both have 8. And then
this is an example of an octet for oxygen. So as you can see, oxygen itself has 1, 2, 3, 4, 5, 6 valence electrons, and then hydrogen has 1 valence electron. But the hydrogen valence electrons combine with the oxygen, and they basically share these electrons right here, so that both oxygen and hydrogen can have a complete octet. And I'm about to draw the chlorine fluoride example right now. Both chlorine and fluoride have 7 valence electrons each. So it might be oxygen and this example is gonna look quite different from this one, but it's still the same mechanism involved. So they both have 7 valence electrons each. But I'm gonna start off with drawing 6 so I can show you how they share those last two, or that last pair. 2. So they both have 7. So this one will be fluorine's valence electron right here, and then this one will be fluoride's valence electron, and this would be chlorine's valence electron, and they would share this valence electron right here in order for them to both have 8 and form a complete octet. See right here and right here. This is my naming for covalent and ionic bonds. So for MgO, because we're doing an ionic bond, you put magnesium first because magnesium is a metal. So you use magnesium, and then instead of putting like tetraoxide or hexoxide or dioxide or something like that, you just put oxide. And this only goes for ionic bonds. So the answer for this would be magnesium oxide. Magnesium oxide. Okay, now we have H2 and S, or we have 2 hydrogens and 1 sulfur. So how we get the name for this is there's 2 hydrogens. The prefix for 2 is di. There's one sulfur, so we can either put mono or we could just leave it alone. So we're gonna have dihydrogen. Dihydrogen sulfide is gonna be the name for this. Another name you could do is dihydrogen monosulfide, but that's optional really. And then we have carbon. We have 1 carbon and then 4 chlorines. So how we're gonna get the name for this is, because it's 1 carbon, we just use carbon. And because there's 4 chlorines, we use tetra to say 4. So it's gonna be carbon tetrachloride. That's gonna be the name for this molecule right here. And this is how you do. This is how you name polyatomic ions, or this is how you name ions in molecules. I'm sorry.